not fun.
How was it?
Yes.
You saw the first one. The ones that he had, the ones that John had, so much better.
That's because
Did you have a job? Yeah.
that was a legend.
Wait, I took this out. But like, he doesn't have any classes in this background, does he?
I have to take computer network next semester.
He goes, sorry.
I'm not taking it. I'm jumping to next semester. I'm switching to next semester.
Yeah, I'm not gonna put myself in that armbar.
I don't know how bad Cyro is. Okay.
I
but
mean,
like,
I had to pretend to shoot. And the next section, there were two sections, one was Cyro and one was shoot. Right. So first two projects were us for separate. Right. Third project is just like I'm gonna collaborate with Cyro. I've been hearing some 60 students who were in her class. But like, guys, don't do it. It was awful. So bad.
oh,
It was
okay.
not a
Okay.
good.
See, the thing I had with I took 310 in the summer with Nova Surya, which was similarly awful in terms of specifications, but like, it's not a hard class, no. Like, I took it as a section with Nova Surya, and it's fine. Kind of descriptions were okay, but they're better than these, which is not a high bar.
I think project description is just go like this. After like this class is project description.
Oh yeah, this class, I mean, again, the class project description, it's not a little bit, probably.
Other classes specifications just go like this. They're like who needs this information?
Except Ozzy's project descriptions are
Legendary.
amazing. Who genuinely Ozzy.
Even Ozzy. He's a legend.
He's the best professor I've met. Yeah.
I don't have.
Oh, okay. What? Wait. What?
I'm CSC.
Oh, all right. Yeah.
Ozzy's a legend. I have Panda Coast is also a legend.
Yeah. No. Ozzy cares so much about the students and
This guy.
Ozzy gets
Yeah.
Don't listen to the
regular
regular professor. He's several orders of magnitude better than that score.
The people who negatively rate Ozzy on my professor, the kind of students who started the whole fight with the projects 2 days before they were due and wonder why it took them so long.
Because those projects do take a fair bit of time.
It tells you that.
He tells you that out of the gate, and like these are hard projects. Like the first one had only a couple percent. Had like I think 20% of everybody getting a 0 or something. Like they just couldn't do it.
He doesn't teach any good classes. I'm going to take it. So
Okay,
he's good.
This, it's not a glass.
No.
I'm just trying to. Really, I woke up explaining how I got the book.
Oh yeah, you also search for.
The man himself, the legend.
Okay, I'm not sure. Because like the other two classes, which is databases and whatever the hell the other one is.
Don't you have databases? Are you taking databases?
I'm probably going to take Cyrus class because that's the only one that has course material that interests me. But on the other hand, it is science.
You're taking NLP. NLP next
I have a feeling classes got to fill up really fast. That's right. You guys are very.
Are you good?
Yeah,
I'm ready. There we go.
I'm in this class.
That's good.
Yeah, I had to go.
This time, easel this way in.
I did.
Yes, you did.
I asked.
Turn the email on. It's the weasel.
I don't weasel anything. I formally asked to be chosen.
October 8th, October 10th demonstration.
I want to take it. They increase the number of seats in that. It was 75 earlier.
Okay, if you go to like further level classes, there's
I didn't take 300.
neither did I. I wish I could take 300. This one doesn't, no. I want to take graph 2D, but no, it's still down. There's like computational methods of image processing and probably reinforcement learning for one of these two, and they don't require 300. I wish I could 300 because
So the one that's at west, that question to the west.
yeah, that's
And the math classes are more. Yep. CC.
I'm probably not taking a after my technical active, but
Eight, whatever class, so.
Are you, Professor Ralph, are you gonna teach this class next semester?
I don't.
really, a great class.
Yeah.
It's too time consuming. What to do?
You're not wrong.
What to do?
Learning is less time consuming.
What are the best machine learning classes in graduate level?
Right now, here. I don't know. Who is teaching the SMF? Yeah, over the weekend, I got excited about maybe teaching a machine learning class, but I'm hoping that the feeling will pass. So I don't have to do it. So, but yeah, there is, I think there's a statistical machine learning class that Eugen is teaching. I think there's a separate. What's the difference? What's the name of the name difference? There's one which is just normal ML, but it doesn't do reinforcement learning, etc. And then one which does basically do and hard statistical learning. You should combine all of them. That's the one that yeah. Yeah. So that's the do down hard. Yeah. Names don't tell you anything.
Do you have any classes in general for graduates?
Ask on the piazza. I will give better answers that way. What?
Possibility like greater than zero probability for you, like.
We're teaching the class.
Yes.
Probably, I don't know.
Is it non-zero? Is it non-zero probability?
I'll let you know. If I'm teaching, I'll definitely let you know. So it's better to see the same people again, which I never get to do much. Yeah, the last time I actually taught a class was fall 19, this class, and then I taught again. Last fall, I just taught honors. To AI, kind of invitation to AI, which was fun, but it was a half semester. Yeah, no, I just do not know how to apportion my time when I'm teaching. When I'm teaching, I'm basically doing just that. And so everything else falls apart. So that's my problem.
Correct.
So yeah, I have taught this course like gazillion times, and then I'm changing again the order in which I'll be doing this time, because I think that's a different way. So next class, we'll be doing something that for the last time we tried towards the end of the semester, which is Bayesian learning, which is basically the theory of learning. That's kind of fun for me. I don't know. It's fun for you, but it's fun for me.
Good at machine learning, or had a lot of us do that.
Oh, let's see. So the basics of why and why machine learning makes sense, you will learn in this class already, honestly. Everything else is details. Those details are important, but you could pick it up pretty much anywhere. Yeah. Okay, so are we kind of ready? Is this time? I didn't get my. That's fine. Okay, so are you recording? Yeah. Yeah, so today and the next couple of classes, we'll still be doing inductive learning or the generalization learning, which we got to from reinforcement learning. And then, so we'll see how far we'll go there. So today's thing is that we will kind of do quick review of TD learning, Q learning with function approximation, which is what we did last time. Then, as I was just leaving the class, I threw in this, oh, you can think of this linear value function as a linear summation of weighted features as a perceptron. So I put them as a perceptron kind of a thing. It's like a network kind of a thing. So I will get back to that and say that it can be thought of as a linear perceptron. In particular, when we were doing function approximation is essentially a task called regression in statistics. Regression essentially means guess the value of the function for a new x value. Okay, if you have an f of x, I give you some values of f of x, then you need to be able to guess the rest of the values. Okay, so that's regression. So function completion is regression. And there's a close by idea called classification, where basically classification is nothing but regression over functions which have categorical outputs. You guys know the difference between categorical versus non-categorical. Categorical basically means they're discrete. Like, for example, a real valued function will always take a real valued input and gives a real valued output. Right? And even if it's a multidimensional real valued function, it takes a bunch of real valued x1, x2, xn and gives a real valued y. A categorical function is one which takes inputs from reals, but outputs are categories, like category 1, category 2, category 3, etc. So there is no in between. So that sort of thing is the one that you might want to think of in classification. So each picture, it turns out that if you think of a picture is a very high dimensional vector, because pixel is made up of pixels. Each pixel based on what sort of the standard you're using is some real number between the intensity of the pixel, basically some real number. Okay, so I'm basically giving you the intensity of all these pixels from here all the way to here. It's a huge, big, very huge, big vector. So now I'm trying to take f of this picture and I want to say it's a cat, or it's a dog, or it's a bus. Those are categories. You see what I'm saying? You could take a function of a picture, and then that gives you, like, for example, average intensity of pixels in the picture. That's a reasonable function. If you do those kinds of things, those are basically real valued functions. That means the outputs are also real valued. Okay? In those cases, you'll think of regression. Whereas if the output is a categorical attribute, right, then you think of classification. That's the difference. That's it. Okay, and then we'll point out that essentially you can get categorical attribute if you have some way of approximating a function that gives a real value. You can always put a gate on top of it. So gating things are what I call threshold functions, are things like this, which basically say up until certain values of the input, they'll give 0. Beyond that, they will give 1. For example, you see what I'm saying? So those are called thresholding functions. So if you take the real valued output of a function, you threshold it, you will start getting categories. Okay. Now it turns out that these kinds of functions, they're no good from our perspective because they're not differentiable. Again, somebody raised their hand when I asked, was there anybody with electrical engineering background or somewhat electrical? Yeah, so electrical engineering basically talks about step function, impulse function, all this stuff, right? So what is a step function? Step function basically is a discontinuous function. But if you know electrical engineering, you know that you can actually convert step function into a Fourier series, which is an infinite summation of sine waves, which are all nice and beautiful continuous functions. When you add them all up, this infinite function up, then you get a nice little step function. Anyway, keep that there, but by itself, step function is not differentiable. So you will start looking at functions like this. That's where that 1 by 1 plus e power minus x comes from. Why is that interesting? Because if you think of minus infinity to plus infinity, and you're trying to draw 1 by 1 plus e power minus x, when x equal to minus infinity, it will be 1 by 1 plus e power infinity. That means it will be 0. Sorry. Yeah, be 0. Whereas at the plus infinity side, it will be 1 by 1 plus e power minus infinity because it's minus x. E power minus infinity is 0. So 1 by 1, which is 1. So it will be like this. And as you increase x from minus infinity to plus infinity, in fact, if you can show that x equal to 0, it will be 1 by 1 plus 2, 1 plus 1, 1 by 1 plus 1, because e power minus 0 is e power 0, which is 1. Agreed? Right? So 1 by 2 is 0.5. So at x equal to 0, it will be 0.5. So basically, this function kind of looks like this. You see what I'm saying? It's a kind of a step. It's a continuous step function. You see what I'm saying? So we will basically consider actually thresholding units, one of which is sigmoid function. There are other kinds of thresholding units. Tan H is another one, for example. So thresholding functions are continuous functions which look like they are some kind of step. Okay, sorry. So Then basically we point out that you can get the classification just by doing a threshold on the weighted sum. Where the threshold is basically applying a G over sigma of Wi xi. I'll go through this again, okay? So now you need to take a differential of d by dw of dou by dou w of G of sigma of Wi xi. So you need to do even more chain ruling, one of which will be knowing G dash. And that's why knowing that if G of x equal to 1 by 1 plus e power minus x, G dash will be nothing but G times 1 minus G is useful. You see what I'm saying? Because the differentials are the ones that take part in the weight update. Remember last time we saw the differential was taking part in the weight update. We'll go through this again slowly, okay? And then these basically, so the weight update will have the differential of the threshold function, the differential of the loss itself, because the way you define the error. Up until now, we looked at only one type of error. In fact, we wanted to look at the absolute value error. And we said, nah, that's kind of too painful. It's not continuous. I mean, it's not differentiable, it's continuous, okay? And then we went with squared error loss. In fact, today, I'll talk about a different kind of loss. So you can define errors in multiple different ways. Squared error is one way of defining error. In fact, we will talk about if you can think of the output itself as a probability distribution, then you might want to compare the probability distribution of the output by the learner to the true probability distribution and take the distance between two probability distributions. By the way, one other thing that you guys have to do, in addition to remembering all your multivariable differential calculus, is by next class, I'll send you stuff. If I don't, please remind me. You better get re-familiar with your elementary probability theory. At least discrete probability distributions. What is a continuous distribution? All that stuff. And what's a conditional distribution? So what is P of A given B? P of A given B is P of A and B by P of B. What is a Bayes rule? Which is basically writes P of A and B as P of A given B times P of B, or P of B given A times C of A, and then equates both of them and writes one in terms of the other. So you can write P of B given A in terms of P of A given B. That's Bayes rule. We'll get to that again if you want to remember later on, but you have to bring this back into your head. You did this. I know that you did this. You may have forgotten, but you have done elementary probability. Probability is extremely important. In fact, one of the things that I'll do next class, I'm kind of doing a bit of a foreshadowing before going into the details, but one of the things that I'll do next class essentially is understanding the difference between compression and learning. Up until now, there's no difference. It looked as if what you're trying to do is you have a big table of values, you're trying to fit a function. And it's so much cheaper to remember the functions than to remember the entire value table. And in fact, in that lecture that some of you saw before last class itself, and the rest of you should have seen by now, I talk a lot about compression versus generalization. You know the difference, but what is the theoretical basis for generalization? And it turns out that the only theoretical basis we have for generalization is in terms of probability distributions. So the idea is there is certain probability distribution over some objects. Using that distribution, you're sampling these objects and you're training your learner. And you're going to test its effectiveness in terms of what it does in unseen examples. It would do well in the unseen examples if in fact it learned the distribution. But notice that while generalization means you should do well in the unseen examples, there is some constraint on what are reasonable test questions. You see what I'm saying? You've taken exams. You've taken lots of courses, you've taken exams. There are times when you think the exam was hard. There are times you think as if you want to set the instructor's house on fire because the exam was not just hard, it's unfair. When is an exam unfair? Remember, exams are extremely easy if the exercises that you do in the class appear again on the test. This is all of your dreams in the night. That, whatever homework problems you have done, that will come. I just have to remember. That is overfitting to the training data. Unfortunately, exam won't ask exactly the same questions. It will change the questions. People understand that. But having taught whatever it is I taught up until now, if in the midterm exam, if I ask a whole bunch of questions about cybersecurity, it's a question. I did not have time to set up an exam. So I saw Adam walking around, I picked up one of his exams and gave it to you. It doesn't matter. Many of you get zeros anyway, so you're getting zeros on the cybersecurity instead of the AI exam. How does it matter? It matters in terms of whether the test is fair. It was unfair because the distribution of the test questions were not from the same distribution as the training questions. We have a very strong sense of unfairness. I tell this, I don't know if I said that in one of the lecture or not, but my wife, who is a faculty member in electrical engineering, remembers this one case where she did a CS theory course back in Maryland, and that guy essentially did half a class at the end of the semester about NP completeness, half a class. And then the whole exam was NP completeness proofs. You see what I'm saying? That's unfair, obviously, right? Because the distribution of the training questions and the test questions were nowhere near. It's like I'm towards the end of today's class, I say, oh, maybe there may be some cybersecurity questions. And then next thing you know, you'll just get an entire cybersecurity exam. It hurt her so much that there was this other woman who is a faculty member at Duke, and they met each other some 15 years later, one day, somewhere at NSF for some panel or something. They said hello to each other. They said, do you remember that really bad exam? This is how much we care about unfairness. When we talk about generalization, we mean it should be able to correctly classify unseen examples from the same distribution. That's the theory of learning. There's compression. There's nothing about unseen examples. It's all about what you have seen, just reproduce it. It turns out that some tests, some techniques work both for generalization and compression. But the real goal is quite different for generalization versus compression. And that's why next class we'll bring this up and I'll talk about Bayesian learning, which is like the right way of doing learning, which is too hard to do. And everybody else tries to do some approximations to it. And in particular, instead of just minimizing the error on the training examples, which is what we have done up until now, you tend to minimize the error on the training example plus some what we call regularization term. The regularization term takes all sorts of different forms. For example, it might say the weights that you use, the individual weights cannot be bigger than a certain value. That's a regularization. Or the polynomial you are using cannot be, you try to keep the polynomial you're fitting to the data to the lowest degree possible while keeping the error on the training data. Do you see what I'm saying? Which is why if I give you points like this, and if you want to compress this, sorry. If you want to compress this, you have to do this. That's the correct compression. If on the other hand, if I ask you to learn the pattern, you typically tend to do this. Why? Because the point of learning is not to reduce the error on the training examples. It is to reduce the error on the test examples. And you tend to assume that things that are kind of falling off of the line are somehow noisy. And that somehow there's a higher chance that the data followed a line than that the data followed a 356th degree polynomial. That's what I'm saying. You guys realize that if you increase the degree of the polynomial, you can fit any crazy kink in the data. If all you cared about is reducing the training error, that's what you do. The difference in learning is it's about reducing the test error. But then if I don't tell you anything about the test, then it's not clear how to do it. I do tell you something about the test by saying, in the normal good learning scenarios, training and test data are sampled from the same distribution. And that captures everything. Like, for example, the distribution of topics that I did in this class had 0 probability for all cybersecurity topics. So finally, suddenly, if the exam suddenly winds up having a whole bunch of cybersecurity questions, then you're not from the same distribution. So this actually brings up a nice little term that people use, OOD. When you do badly in learning, in test, you normally say it's unfair, etc. But real machine learning people say it's OOD. It's out of distribution. How the heck did you expect me to do well in out of distribution test? Okay, this is where we are going. This is the bigger picture of what we'll be doing this class, next class, and maybe a little bit of next class. In doing this kind of learning is where, there are many techniques. One of the techniques we'll look at is multi-layer neural networks. Perceptron is just a single layer neural network. Questions? Okay. Yeah. So that's basically what you should be able to get by the end of today's class, assuming that I get through all of it. And again, I did ask people to tell me what's going on in the class. I think 3 people took time to tell me. And, just like Rate My Professor is mostly written by people who are pissed off with the class, right? This apparently is only done by people who love the class. So I will make my assumption that this is the distribution. Everybody is happy. Behind the masks, you're all just loving this class. If you don't, you should tell me. But because these are the kind of stuff that I'm getting. And I know that these other classes and things like life, those are the things that get into the way of enjoying my class. I know this. People shouldn't have a life. People shouldn't have other classes. Then, we'll just do one thing very well. I'm kidding, of course, but, I understand that feeling. And, that's probably something that I could live with. Okay, this refresher, I told you guys should do. So very quick refresher from last class. So we are to remember how quickly we're shifting. We were doing reinforcement learning 2 classes back. And we did temporal difference and Q learning algorithms tabular versions 2 classes back. Those tabular versions essentially had a Q value for each cell, each state, there was a cell in the table. And you basically replace that value by the value that's nudged towards the actual neighbor that you wound up experiencing during your experience in the real world. This is what we were doing, right? And then we said, hey, there's just too many states. We want to generalize this. We want to represent the value function as some sort of a linear, some sort of a function, values in the cell as a function. Functional representations are compact often, can be compact. In the worst case, a tabular function is a function. But you still need to tell me what happens in the unseen values of X. Okay, so I assume that if you have some features for the states, then I essentially took a weighted, all features are real valued features. And I took a weighted sum of these features where the weights in this case are thetas. Normally you either use W's or thetas. There's a big convention in machine learning community that comes from statistics that tends to think of the weights as thetas. That makes you look a lot more sophisticated Greek person, I guess. So if you want to look like some kind of a, sort of unwashed American, you can say WI, which is good enough as far as I'm concerned. But theta I, if you get very worried, you can write a whole bunch of WI stuff and replace W by theta instead of N. Basically, it's just a symbol for the weights. Okay. Typically, these are called parameters. Right? They're called parameters. You're learning what is the best thetas that you should pick such that you can multiply the current state's features in terms of these thetas. While every state has different feature values, potentially, the weights are the same across all the states. So you only get one chance to figure out what the right set of weights are. That was the nice part. And so we do this, and then basically we try now while we're doing TD learning or Q learning, instead of changing the cell of the Q table or the value table, you change thetas. And thetas are the ones that you can ask the theta guys, once you know the function, you can ask what should be in this cell, and they'll tell you, yeah, this is it. People understand this. This is very crucial. It's very simple, but it's also very crucial to understand what's happening here. Yeah.
If you're not given a set of outputs or boards, could you compute data values still from a given data set?
No, so right now, so what you're talking about is this idea of unsupervised learning. We won't get into that. So right now we are assuming essentially that the value function, correct value of the value function is known for the next neighbor in essence. And you're just trying to come close to it. Okay. Yeah, so then that's what we were trying to do. And basically what used to look like a normal change the value in the table for the Q values and the V values now looks like update the thetas. Every time, whenever there is a transition, previously you used to update the table. Now you just update the thetas. Right? And then the point, of course, is that is a mind-bending pivot as of last class. Because there is this question there's a pivot from atomic state representations to feature-based state representations. I went a lot about this. So you're representing states not by their social security numbers, but by their features. And that brings up the question, who gives the features? And I talked a lot about, for now, assume humans give the features. Okay. More ambitious would be to let the system learn the right features itself from the raw input, which in the case of RL, that is basically what is called deep RL. What that essentially does is maybe it will just put the pixel values of a picture as the input to some agent, reinforcement learning agent, which is then trying to make decisions based on. So this is the basically the input it's getting is pixels, not a feature-based state. And if in fact we will talk about this as we go forward, but if in fact the learner inside is a multi-layer neural network, you can think of it as learning from pixels some things like edges, from edges some things like textures, from textures something else, and finally the class. Is that what they're doing? No, I don't know at all what they're doing. We don't actually know what they're doing. You can sort of make sense of it as they're going from pixels. In some sense, that's what we must be doing. We're looking at the world as pixels, eating our retina. We are still thinking of the world in terms of objects, relations, and so on. Somewhere along the line, that transition must be happening. So DRL basically goes that way. And so what that basically means is it takes like a gazillion more experiences to get to the same level of performance as reinforcement learning, which has hand-given features, handmade features. So you have to be particularly masochistic if you try to do things from pictures when you actually, for let's say, Pac-Man, when you can talk about things like number of goes, and the coordinates of the Pac-Man, all that stuff. Because remember, all those things, number of goes, coordinate of Pac-Man, etc., are essentially some complex function of the pixels. Because that's what you're doing. You're looking at the picture and saying, oh, there are 4 goes. How did you figure that out? If you could figure that out, some random machine learning algorithm can figure that out too. It might take forever. I mean, you got where you are because of evolution. Deep learning is evolution sped forward and hoping for the best. Okay, so that's one part. So for now, we'll assume it's hand designed by us. The second pivot is from discrete search to continuous search. Up until now, we've been talking about search in terms of A-star search and MDPs. Also, we looked at discrete MDPs. All algorithms were discrete. But basically, if I'm thinking of what should be the best thetas are real numbers. So I'm looking for the best vector, theta vector, which one is dot producted. By the way, this is the other version. Do you guys remember dot product? I mean, do you know what dot product is? The dot product of a vector, let's say V1 is x1, x2, xn. V2 is y1, y2, yn. Then V1 dot V2 is x1, y1 plus x2, y2 plus x3, y3 plus xn, yn. That's the vector dot product. Any of you actually done vectors like some time back? Yeah, that's vector dot product. So you can actually do what you're doing here in a simpler, what is happening here in long form can be written as the theta vector dot with the f vector. F vector is the feature vector. Theta vector is the values of all the thetas, all the weights. What you're trying to find out is the best theta vector. The question, of course, is what is the best theta vector? We basically say that the best theta vector is the one that minimizes the error with respect to the true values. So that's why we wound up writing the squared error differentiating that to get the gradient, and then write the changes to thetas in terms of each theta will be shifted in direction opposite to the partial derivative of the error function with respect to that theta value. Okay, so okay. Anyway, so this one is basically some work that we are doing above, which basically does DRL, but I won't go into it right now. So for TD-based RL approximators, essentially you will have something like this. The temporal difference learning algorithm will just be changing theta in terms of the old value of the theta plus alpha times the gradient. I mean, basically negative of the gradient. Okay. And similarly, for the Q function, it would be like this. In fact, there's not much of a difference. If this is the Q function approximation, Q value update with function approximation. And this one is tabular. We saw these two classes back. The only difference is previously you are updating the value of QK plus 1 in terms of the neighbors Q values. Here, you're only updating the thetas. When you update the thetas, everybody changes, including the QK plus 1. Yes.
What does the beta represent?
Okay, so I'm sorry. So this one is, think of this as, so there basically this particular slide wound up having a different notation. So let me just write this as R S A S dash plus gamma times max over A dash. Beta, some people use beta for discount factor. And some people use, as I said, RS instead of RSAS dash as the reward function. If I wrote that in terms of this, I could be like that, in terms of RSAS dash. Now, the other thing that you want to understand is what were we doing this in this case? What we were doing in this case was, let's see, yeah. What we were doing in this case is this, which is we considered basically what's called an online generalization. I didn't use the term, but that's what we wound up doing, because in Q update, Q learning and TD learning, there is a kind of a current value function. One more new sample comes because you did an action, you got a new sample, and you're trying to nudge yourself to be closer to your sample's value, a sample's Q value or value, right? That's what we've been doing. So you're doing it one sample at a time. And the entire derivation, if you remember, I wish I could show it here because I actually hit them, but the entire derivation is in terms of error between what is the true value for this one sample and what is the predicted value. Where the predicted value is in terms of thetas. And you're just using that error, sample, one single sample based error, to change the thetas or to change the W's. This is what we did. This is what makes sense for reinforcement learning, because experience comes one step at a time. You could do this other third thing, which is, you know, instead of just changing theta values for every experience, I will do like 5, 6 experiences and do theta values one theta value change for the batch of those experiences. That's possible. So that means you kind of hang around. For every action previously, you are changing your theta values using the theta update. Here, you do some number of experiences and then do theta value update. We didn't do this last time. If you are doing this, what happens is that the error over these k samples has to be minimized instead of error over one sample being minimized. Do you understand the difference? Previously, we were just minimizing the error over one sample. Now we are minimizing error over k samples. Even this would make sense for RL, kind of makes sense. Kind of makes sense for RL. There's a third idea, which is wait until the entire value function is ready. So that means just run the value iteration, TD update or the Q update until you're sick of it. Basically, it converged. At that point, learn the best function that represents the learned value function. Do you understand what I just said? If you do this, you call this online. I'm sorry. If you do this, you call this online or what's called stochastic gradient descent. If you do this, you are doing what's called a mini batch gradient descent. If you do this middle one, you're doing the full batch gradient descent. That means you have the entire function that you need to approximate. I mean, all the training samples that you'll ever get are given upfront. And so then you can try to separate, compare different functional approximations by taking the function that minimizes the sum of the squared errors over all these samples. You see what I'm saying? And then use that to update the theta. And then update it again, and update it again, update it again. Because every time you update the theta, you're changing the function. So the derivative changes. Okay. This is the full batch. And it's a dumb idea for RL. Completely dumb idea for RL. Why? Because you did all the hard work essentially at the atomic level, and just to impress some boss later on, you just basically converted it into a functional form. The reason actually function approximation with RL is such a great idea is it not only speed, it not only compresses the value function, it is also changing the values in multiple places at the same time. When you changed the thetas because you just had one experience going from S to S dash, that changes the current value estimates for every state in the table. If you're good, this might mean that you will converge with much fewer iterations. If you're bad, it means that you will do a lot more crazy going around. Which is why when the function approximation idea came along in RL, for the longest time, there was no theoretical guarantees as to when function approximation will actually get this absolute, the V star value. Okay. Now we have reasonable guarantees, but again, as I said, computer scientists are people who at least once in a while think about guarantees, but then they just do it anyway. Okay. This is what we did last time. And by the way, this is mini batch, this is full batch, this is a stochastic gradient. And even though we did all of this coming from RL and trying to learn the value function or the Q function, the technology we are using is general technology. It's basically function approximation. While in RL, batch gradient is a dumb idea. In some other scenario, let's say you basically have a whole bunch of credit card transactions that you have done. I mean, a whole bunch of credit card transactions that somebody has done, and you are trying to predict what should be their, what is this thing called credit worthiness. There's some credit score, which is a real number. Going for a real number right now. Credit score is a real number. Right? So they will give a whole bunch of people and their credit card transactions and the credit scores. So you can learn a function by looking at all of them and look for the function that minimizes the prediction error. There's no advantage in looking at things one sample at a time in that case, because all samples are in front of you. Right? So it turns out that for the longest time, when you do this sort of a stuff for simple regression learning, where you have a bunch of training samples and you're trying to fit a function, where in RL training samples come one at a time or k at a time, but normal learning, they can be all given upfront, unless it's a particularly online kind of learning. You see what I'm saying? Okay, so you would basically think that for those guys, this would be the clear winner. Batch gradient must be the clear winner. That's what people thought for the longest time. It turns out, it's a strange thing. It turns out that even if you have all the examples in front of you, you are better off doing stochastic gradient descent. As if all the examples are there, but you take examples only like one at a time or a few at a time. In doing so, obviously, there is noisy update procedure going on, because thetas, if you look at the error on all the examples and change the thetas once, then more likely they would be changed consistently towards their right values. Whereas if you look at one value at a time, they will be jumping all over the place. One of the strangest things is there are both practical and theoretical results saying that this wins. Stochastic gradient wins. So one of the other things that you should remember, SGD, stochastic gradient descent, which is, even though you have all the examples, you're doing either one example at a time update or mini batches, buckets of examples at a time update. Okay. Questions? Yeah.
And what about the credit card example?
Yeah.
We want to do this then in SGD too? Like what?
Yes, that's what I'm saying. Everything. In general, it turns out SGD, for large problems, SGD converges to the right weight values faster. Right weight values faster than I should have changed. Right weight values faster than taking all the examples. This is unintuitive. It's unintuitive, right? I'm saying you have all the examples. You want to look at all of them at the same time. But it turns out actually looking at them few at a time, as if they're giving them piece by piece, is actually better. People use this to make all sorts of crazy metaphorical statements about the world, because now SGD has become such a big thing in general. I will talk about those if you remind me later on. There was a question.
What would the equation, the update equation look like?
We'll be looking at some more update equations. There's not much of a difference, but we have done one already last class for the single example case. Today I will do for the summation case, and you will see there's no difference. The summation is linear. Okay, so this is stuff that we did. Unfortunately, things have messed up here, but I did this by hand, and I also have better correct slides in the setup. And then I did talk about viewing this whole regression in terms of perceptrons towards the end of last class. And that if you basically have F0 to Fk, and then you have theta 0 to theta k are the weights on these edges. So you basically sum theta I Fi, and that would be the output coming out of this perceptron. Except actually, since I'm into this, I will say that this guy, I'll call this a quote unquote neuron, wink wink neuron. It's not real neuron of the kind you have. It's sort of inspired by that. And what neurons seem to do is this much we know about neurons. This is how a neuron looks. And neurons are connected to other neurons using synapses. And this much is known that when the input activations, incoming activations for the neuron cross some threshold, the neuron fires. You heard of this neuron firing? Firing actually means thresholding behavior. Guns are thresholded. If the gun is all the time discharging, it's not a fire. It's not firing. Do you understand what I'm saying? So essentially, neurons will basically wait until the input activation is certain value, then they'll fire. When they fire, their activation is then sent on their outgoing links to other neurons. Which is why in all these Hollywood movies, there are all these nice little dots and major numbers of lightnings are going all over it. And you say, oh, that's playing all right. That's the cartoon version of neuroscience. Right? So one thing that we do know is neurons do thresholding over the inputs because they have to wait until the some sort of a weighted sum of the inputs is above a certain value and then fire. This is where those thresholding functions that I was talking about come, and this particular one is your sigmoid function. I'm not saying that your neurons use sigmoid functions. I'm saying in this story, if you want to follow this story, this kind of thresholding behavior makes sense. We actually would follow this really because we want to do not just regression, but regression and classification. That's one reason. Another way more important reason that we will come to next class when we do neural networks again is in fact that if you stack perceptrons, that means one perceptron output goes to another perceptron's inputs and so on and so forth. So you have a stacked perceptrons which will look like a deep network. One funny thing is if all these perceptrons are linear, that means they're essentially not changing the weighted sum of their inputs by any thresholding. Then the big perceptron is also a linear perceptron. Because composition of linear functions is a linear function. Whereas if you throw in one nonlinearity in every one of the basically the thresholding, then if you compose nonlinear functions, then you can get overall nonlinear functions also. And since sometimes you may want to fit nonlinear functions rather than linear functions, you need this ability. And the most mind-bending thing we will get to some classes from now, like 2 classes or 1 class from now, is that any neural network, that means any stacked set of perceptrons with a nonlinear threshold unit, if it is at least 3 layers, that means there's an output layer, there's a middle layer, there's a final layer. Just 3 layers. Then any function in this world, whole entire world, can be approximated to any degree of accuracy by such a network. Now you might be thinking, what is he trying to say? I never told you about how wide the network may be. I'm only talking about the depth. an infinitely wide, potentially infinitely wide 3-layer network is able to approximate every continuous function. 4 layers, you will get discrete functions also. I mean, discontinuous functions also. So that is really the reason why people say, if you just keep looking at neural networks, eventually you will find an approximation to any function in terms of neural networks. But the electrical engineering guy wouldn't be impressed, because that's true of Fourier transforms too. You see what I'm saying? It turns out that any random signal can be represented as the infinite summation of sine waves, weighted summation of sine waves. It's not surprising. It's just that the basis vectors that we have here, which is basically these threshold units, do have that expressiveness. And that's why just sticking to them will still not sink you. So those are the 2 reasons why, instead of just taking theta I fi sigma and then trimming it out, I will pass it through a g function. G is the thresholding function. It could be things like 1 by 1 plus e power minus x. Okay. So if I were to do this, then look, this is almost basically close to what we did last time. If the G is identity function, then what we did last time is this. The only difference is last time we assumed examples come one at a time. Today, I will try to do a version where examples are all given upfront. All training examples are given upfront. And so I take the full sum square error and minimize that. And you'll see that it almost looks the same in terms of the math. There's just a bunch of sigmas floating about. Okay, questions? Okay. So I already mentioned this, regression versus classification. Classification essentially, one of the other reasons, the 2 reasons we had for thresholding functions is, one is for doing classification, because thresholding functions can convert continuous input into discrete output, close to discrete output, categorical output. Okay. The other is, of course, as I said, if you do throw in a nonlinear threshold, then basically the nonlinear threshold, the stacking of perceptrons, even 3 layers, will be able to approximate any continuous function, theoretically. That, by the way, that theoretical guarantee is sort of like the other theoretical guarantee I'll tell you, which is, how many of you heard of this naked Greek guy who ran around Athens called Archimedes, saying Eureka, right? Why did he do that? Because he learned, actually no, in fact, he did this for the density, relative density part. But one of the other things he learned, he figured out, is the principle of lever and fulcrum. That means if you put a lever and you have a stick, right? Then if you have a longer edge of the stick this side, shorter edge that side, little force here magnifies that side. There's a story that these other bozos from the other Greek city came and kept their ship outside, and carefully Archimedes constructed a fulcrum, got a huge big stick, put the short end underneath them, and they were still waiting, seeing what's going on. And then he pushed this and the ship fell over. If you don't know science, this is what happens. The first guy who learned science can just decimate the rest. Right? So then Archimedes got drunk with this power of leverage. And there's this picture I will show you next time. And he said, give me a long enough stick and a fulcrum, I will lift the universe. I'll lift the universe. Because that means also you can also lift the earth. Theoretically true. practically no hope. Exactly where are you going to find a fulcrum and where is this long stick coming from? It's one thing, throwing like a Dumbo guy's ship in Athens harbor. That's the kind of thing we mean by this theoretical result. That basically means there exists some infinitely wide 3-layer network that will be able to correctly reduce to approximate any function to an arbitrary degree of accuracy. It's the same kind of thing that Fourier transforms have. Anyway, so classification basically is used for classification. We need this threshold thing. That's also important. And in the case of perceptron, so this is the perceptron that we'll be looking at today mostly. But notice that this is useful. And if I'm thinking for right now about classification task, that means essentially I have some kind of a G here, some threshold, which then takes the sum of inputs and says either 1 or 0 comes out. 1 means class 1, 0 means class 2. It's a binary class classifier. So this is called binary class classification. By the way, one of the other negative things somebody said is I'm writing too much stuff with a red pen. So today I'm reading only stuff with green pen. So at least that person should be happy. Okay. So you can tell me these kinds of things. I mean, easy things that I can do. Okay. So if you have multiple classes, that means you want to be able to differentiate between is it cat or not cat? One perceptron, one binary valued perceptron. If on the other hand there are n classes, it can be a cat or a dog or a porcupine or whatever, random other animal, k animals. And I still want to do it with a perceptron. It's not a question of is it a good learning algorithm, but can you even use it? Well, you can use it this way. Where essentially all the inputs are fed to every one of these output nodes with different weights. You guys see this? And then presumably this is the dog guy. And if this guy ever lights up, that's a dog. And this is a cat guy. This is a porcupine guy, etc. And of course, the question is, how do you train this network? Right? We'll get to that later. In particular, this is the place where we will have to go out of simple mean squared error and think of these numbers here probably as a probability distribution. If you think of these numbers, that is because it's like all these things will light up with different intensities. If this perceptron is amazingly good, it will put 1 for, if it's a dog, then it will put 1 for dog and 0s for everybody else. If not, it's more likely it will put like a 0.8 for the dog, 0.002 for the cat, and all this various other stuff. Just 1 second. In fact, this is known to be the case that ImageNet does top 5 accuracy. On the ImageNet competition, which basically was the reason people got interested in neural networks, when they say it is accurately predicting, what they're saying is if the true class is one of the top 5 classes in terms of the probability, you get a point. This is the kind of thing that you hope on the exams, right? You get to write various number of answers, and if any of them is right, I should get full points. That's the top 5 accuracy. I mean, it is true that people who can't even guess it in the top 5 are worse than people who can get it in top 5. But the people who can get in top 1 are the best. Right? Yes.
So you mentioned thinking about the outputs as a probability distribution function, but wouldn't it not necessarily be the case that they all have to add up to 1?
That you can do, right? Because you can always convert any set of real numbers to a probability distribution. Okay, so that's a minor technical. Okay, by just normalizing the numbers. That's basically it. Okay, so in that case, when we have this, we actually use what is called a cross entropy error, which I was going to show you in a bit, but I'll show you at least once today before I do what I was planning to do. Yeah, so a cross entropy, I mean, I'll do this again next class. A cross entropy thing essentially looks at the true probability distribution and the probability distribution that this network is computing, and sees the distance between the two probability distributions, and it minimizes that. The only reason I'm showing you this is it's not that error has to be always a squared error. It actually, a squared error itself was a stand-in for the absolute value error. And you can do cross entropy error. There are all sorts of other errors. In fact, there's an entire cottage industry of loss functions. Loss is like a big name in machine learning. Loss is error. What you said and what is true, and the difference is the loss. And you have to compute some function of it. And irrespective of the loss function, you will need to then find the update rule for that. Okay, I'll go back from this, and I want to now, in the next few minutes I want to show you two things. Actually I have 10 minutes, so let's see if we can do this. But essentially, I want to show you this slide. Oh my God, this is so bad. Basically, then this is the same reason everything is gone away. But I'll put the right version of it, but I'm actually going to do it by hand the next 10 minutes so that you will go through it slowly. Okay, I'm doing the same error because the stuff that I can see on my laptop can't be seen on iPad sometimes. Okay, so in essence, what I'm trying to do here in this, if you can see this slide correctly, you can't see this slide correctly on iPad anyway, is that I'm actually computing error. I'll do this in step by step. I'm computing the error in terms of a squared error. I'm only doing it for a simple single layer neural perceptron, but I'm actually going to be doing sum over all the errors, and I'll try to minimize that. Okay, let's see if I can do this steps quickly. Okay, so I have this network, and these are Wj weights, and these are the Ij inputs, and there is a G function which is going to threshold summation of Wj Ij and then outputs. That is the O output. And I've been given a whole bunch of examples. All the examples are in terms of I1 to Ij, and I know the function value for them. In this case, because I have threshold, I can just assume that it's most likely going to be between either close to 1 or close to 0. There is G is a non-trivial threshold function. If G is identity, it will just be a normal real number. So there would be a function value here for each of these inputs. And so we will call that T. For each Ij, there is an actual function value, or what typically people call label if it is a classification task. That's the true value or the true label, minus what the machine thought. Minus what the machine thought is the value. This perceptron thought is the value. And I will square that, sum it over all the examples, all the training examples. Then the usual thing, I'll do half, because I like to cancel 2. This is the error. And this O is nothing but, in fact, if you write it down fully, the error is nothing but half sigma I. T is the true value. You read it from here. But O is nothing but G of sigma j of Wj Ij. Do people get this? Right? That's what it basically, this is the true value. this is what the perceptron will say. And what it says depends on the W values. And it is these W values you want to change. So the error is a function of Wi. Error is a function of weights. It's a multi-dimensional function. If there are k weights, if there are 2 weights, it would sort of basically, if it's a two weights, then it will look like this: W1, W2, and error in this 3-dimensional space. It's an error surface. You're trying to find the minimum of this error surface. One interesting question would be, when does error surfaces have exactly one minimum? In the simple linear perceptron case, the error function would sort of look like this nicely. You see what I'm saying? So because of which it turns out this is the convex, it's called a convex error function. Convex error function only will have one minimum. And so if you do gradient descent with a reasonable enough alpha descent, you will find the minimum. You might overshoot it, come back, but you'll find the minimum. In other bad cases, this function might be multiple minima. And there is no guarantee that you will find the lowest minimum. You'll find one of the minima if you do gradient descent. Okay, right? So I have this. Now I essentially need to take to E by dou Wj, the partial derivative with respect to Wj. Okay, that would be that 2 will cancel out because this whole thing is being squared, right? So the 2 will cancel out, and in fact it will be minus, and then this whole thing is, you can write this as t minus o square, so it will be 2 times t minus o, the differential. So I'll put t minus o here. Okay, and then I will have to differentiate g. I'm doing chain rule. I have to differentiate g, so I have to do g dash of this. I'm doing chain rule. There's a whole big square. First take 2 of that, and then you take the g dash. Then you take this one, and you finally differentiate it with respect to Wj. If you differentiate this sum with respect to Wj, the only thing that will be left will be Ij. Right? Because everything else, differential of W1 times I1 with respect to Wj will be 0. W2 times I2 with respect to Wj will be 0. Wj times Ij with respect to Wj will be Ij. This is the part we did last time. The only thing that's different is this g dash part. You see what I'm saying? So all then I need to do is the weight Wj is now going to be set to Wj plus Ij times t minus o times g dash. This complex thing is just a number. You know g dash. G dash is, if the sigmoid, it will be g times 1 minus g. And this is the x. And you know the current values of w's, current values of j's. Okay? And then all I then need to do is basically I need to consider, put an alpha. That's the rate at which I'm changing the w. This looks almost like what we did last time, except that I had to also differentiate g dash. Yes.
What happened to that outer summation over the eyes?
What happens to the,
The one that's like right after the 1/2?
that is, okay, wait, so. Yeah, so this one is, you would do that for each one, right? So, I'm sorry, there is a, that outer summation is still here. No, this is not WJ. I think you need to sum those errors. I'm missing a sigma here. Let me double check and get back to you. But again, that sigma, so what he's saying is this summation over I. It is done for each one of the examples. But for each example, you are still doing it with respect to, you're trying to still doing it with respect to WG. Let me get that back. It's too late right now to answer that correctly. I will do that. So the only thing I want to say at the end of today's class is gradient descent updates always looks like this. It's always the same form. W basically is Wi minus alpha times the differential of the error with respect to the weight function. And it depends on the error function, the G function, the actual ith input value, the differential itself. And every time the error function changes, the differential will change. You could do this step by step for everything yourself. Or since differentiation is pretty much a science, you can do what's called auto differentiation, which is if you write the function in some computational graph, then on that same graph, you can do a backward flow, essentially computing the differentials and changing the weights on the way. That's what modern neural networks do. We'll stop here. I'll get back to that sigma question that the student has, check out my name. Okay. Thanks.